This session is a little bit about how we solve TLS cross-host session resumption through NGINX Lua. My name is Ziling. Here's a little bit about me. I'm a system engineer at CloudFlare. Basically, I touch everything about TLS layer. I do NGINX OpenSSL. I also do CFSSL, a toolkit we developed and open source for everything you need for TLS and certificate, all those kind of things. I also touch internal system security infrastructure at CloudFlare. So basically, I do everything about TLS. I haven't made it up to HTTP yet, so but we're going to talk about TLS today. Here's the agenda. We will start with TLS Handshake. What is TLS Handshake and why we want to do TLS Session Resumption? And in the next, I will talk about why we want to do cross-host session resumption, because that's actually another outstanding engineering problem. And we will present our solutions as session resumption by NGINX Lua. They actually support both session ID and the session tickets, and we will see they actually are two different solutions. And eventually, I'm going to talk about how we make one more step at CloudFlare to solve our internal problem with these cross-host session resumptions. I'm going to talk about a lot on keys, so that's what the picture is about. So what is a TLS handshake? A handshake here means a series of a series of message exchange over the network, right? It involves two parties. One is client, one is server. Just like this. Okay. Doesn't work anyway. So you got the idea. These two cats are doing some serious handshake there. So what is actually a TLS handshake? Initially, we just think about a client and a server should come up a mutually agreed keys together. The client will generate the client random and send the client random through a client hello message. Server will generate a server random and send the server random through a server hello message. And the third step is the client is using the server's RSA public key to encrypt a pre-master secret and send this pre-master secret over the wire to a server. Server eventually using the private key to unencrypt the pre-master key. Eventually, the session key is a combination of client random, server random, and pre-master key. So this key will be changing. It will be different for different handshake, because you think the client will use different client random, server will using different client server random, and also the pre-master key will change over time. But there is a weak spot. The weak spot is at the server side, the RSA private key. Basically, if you're using the same the public RSA public key to encrypt the pre-master secrets, the pre-master secrets, once you got the private key, the pre-master secret is no longer a secret. And actually, because the server and the client random are sent over the wire in the plaintext, basically you can get every session key after you get RSA private key. So this is not secure. That's why we move on to the next stage of TLS handshake, and we often heard about is ECDHE. What's DH here is Diffie-Hellman. In Diffie-Hellman key agreement, the pre-master key generation is a little bit different now. That the server will generate a Diffie-Hellman parameter and commit a secret through the Diffie-Hellman parameter as this blue box. And the client will using the same Diffie-Hellman parameter and generate the client's secret and commit into this red box. Eventually, the pre-master secret is a combination of the red box and the blue box. There's some crypto mathematics there, but you will get the idea that it's a combination of these two honest secrets. So what we get here is now the golden session key will be secure from the single point failure. That even though you get one session key, or even though you get one pre-master secret, you are no longer able to get the next pre-master secret because there's no single point of failure of that private key there. Every time you get a new key, so we call it ephemeral DHE. So everything looks fine right now, but there's a problem. The people who don't know is TLS Handshake is expensive. How expensive it is? We have data, right? If we talk about RSA, we have RSA decryption operation at the server side. Obviously, we only can handle hundreds of operations per second. This is talking about one core. Of course, you can do multi-core, but you can only scale linearly. Like how many cores you can have? 100 cores, maybe. Or if we move into an ECDHE, then we get a magnitude of 2, a multiplier of 2 of efficiency basically here. It's not dramatically big enough. We're still talking about hundreds and thousands of operations per second. That's how the server can be at best. And there's more about the TLS Handshake is it's a 2 round trip protocol. Basically, when we talk about network latency, we want to reduce as much round trip as possible. If we do coast-to-coast handshake, we are talking about hundreds of microseconds. If we do local connections, we talk about tens of microseconds. And of course, we want the latency to be as small as possible. And of course, that's where the CloudFlare is doing is we try to reduce the network latency layer. So in order to make the TLS Handshake not that expensive, we're thinking about a session resumption here. So what is session resumption? Session resumption basically says if the client and the server has already negotiated a session ticket, a session key already before, can they reuse the same key as long as the client still remember the key and the server still remember the key, right? So we already have that in the TLS protocol that the server is responsible to assign the session ID to every TLS handshake. So when the clients come back to the server, client can say, hey, server, do you remember me? Because I was using the session ID number 2 that we previously using. Server supposedly should get this session key from a local cache using the session ID. Also, the problem now is if we are going to handle a lot of clients here, clients say we have 100,000 sessions concurrent together, then the server is talking about a much bigger phone book basically here. We do some mathematics on the back of envelope. Basically, if we want to handle 10,000 sessions per second, and you want to keep the session for example, an hour, and every session is about 100 bytes, we're talking about 3.6 gigabytes of storage. And that also scale linearly with any of those factors. So if we're talking about more connections, or we want to keep the session in more a little bit longer in the cache, they all contribute to these memory consumptions. And remember, this TLS handshake is not come up as today, and we all think that memory is cheap. It was like 10 years ago or 20 years ago, people are talking about, we want to reduce the resource consumptions. So we get this next stage of the session resumption. We have another mechanism called session tickets. The basic idea is if server is expensive to handle the storage of the sessions, how about let's let client to do that? Because we already have, for example, tens of thousands of clients, and each of them should store a ticket. And that will reduce the storage at the server side. So what the server does is it will use a key called ticket key, and using the ticket key to encrypt the session key. At the end, you get this session ticket, and you hand over the session ticket to client and says, please keep this session ticket. And if you want to resume the session, you present this session ticket to me, and I can use the same key as the ticket key to decrypt the session ticket and get the session key from the session ticket. Therefore, the server doesn't need to keep any state. The server only needs to keep one key, and that's much better as we consider it's a distribution of the storage. And at the end, we do some benchmarking of the session resumption, right? This is from client side, but server side is basically the same. You've got an idea. On the left-hand side, you see the network latency is cut in half because, of course, we reduce one round trip out of two. On the right-hand side, you see because we don't do any crypto operation layer, you're basically just talking about free session resumption on CPU, on the CPU time. So we got two mechanisms, and it all works pretty good. Now we come to this problem is we are talking about multi-clients already. So how about multi-server? If we want to have multi-server and we want to do session resumptions, we have a new problem. If we have two servers here, each server maintains its own states, its own cache, its own key. You negotiate the TLS session with one server, and you try to resume this session with another server, you just get a fail. And also, the problem is if you try to scale up, you want to have more servers. The more server you have, the less value it is because it's a simple math. You're less probable to hit the same server. So at the end, we really need to do cross-host session resumption at CloudFlare. And also, there's another question is why want to support both mechanisms? Because some browsers doesn't support ticket key yet, or session ticket yet. If you go to howsmyssl.com using your iPhone or your Mac on Safari, you probably get a big red bad sign on the session ticket support. That's why that we still are looking for, as a client server side, we want to support as many clients as possible, right? As the number says, we have 40% clients still using session ID and there are no session tickets, and 60% of the sessions are using session ticket. So they are not like we can choose from one to another. We have to support both. To do this cross-host session resumption, let's look at ID first. In ID case, that means all servers, they have shared one session cache. They will use the same yellow book to look for session keys. And the session tickets, in the session ticket case, initially it looks a little bit easier because if every server shares the same key, its session ticket resumption is achieved across multiple servers because you can present a ticket to any servers, the server can decrypt it, and problem solved. However, we still have a problem of a forward secrecy. Remember we talked about RSA, TLS Handshake, that we have a single point of failure. Here is another single point of failure. If an adversary gets the ticket key, he basically can, or she basically can decrypt the ticket key every time. There's no secret or there's no forward secrecy anymore because once you get to, once you are able to decrypt one session ticket, you are able to decrypt all session tickets. So what's the problem? What's the solution here? Of course, we want to rotate the session key very often, every now and then. We have, for example, we should try to have a key schedule saying for every 1 hour, we will use a new session ticket. Sorry, a new session ticket key. And we want to use we want to have these new keys to propagate to all our servers. So those servers will share the same key, right? And then we solve the problem of forward secrecy because every time if we rotate the key, the server will use the new key to re-encrypt the session ticket. You're going to get a new ticket for all sessions. So for the adversary, even though adversary can get one session ticket key, the adversary cannot decrypt all the sessions. So here's, at the end, is our solution. Basically, we think about how we can do a cross-host session resumption that support session ID and the session ticket. Essentially, we want to have a shared session cache, and also we want to have a shared session ticket key schedule. So what does that require? Basically, we're talking about we want to have NGINX server to talk to a shared key store, preferably through a memcached interface. We want to talk about the performance of such session resumption. We want to do the non-blocking I/O with a session or ticket key. We also want to do want to enhance the performance because we cannot afford a latency of a network to get a session or a ticket key because it's just too expensive. So we want to do multi-layer caching that at server layer you have a cache, at the worker layer you have a cache, and eventually at a server layer in the cluster level you have the same cache. Also, the other requirement is the security, because if we think about we are going to store all sessions in this common place, in this like memcached server, I want to do some basic protection of that memcached server. I cannot just have every session being live in the memory at that server, and somehow if someone breaks into that server, we just basically hand over all the keys to the attackers, right? So we want to do security. At the end, it's also the usability. That if as a software developer, we always want to add new features to it. How can we do it? We don't want to say, I code up this code and it cannot be changed over time. It has to stay as it is. So we want to do easy to maintain configurations. And so, of course, we think about some, initially my instinct reaction is doing it in C, right? For example, for shared memcached key store, session store, how about we do a new NGINX conf module? It's pretty standard. We want to do a new config. So I searched on GitHub, and I got something. It looks okay. It has 600 lines or 700 lines of change, but it doesn't take the account of blocking I/O in it. I still need to research my own solution of session encryptions, and there's no test. That's one problem of you are going to fork NGINX is NGINX doesn't come with test. So what we do is actually, of course, CloudFlare has a very strong presence in OpenResty that we just do it in OpenResty. In OpenResty, we have already programmed a shared session store, a memcached interface over there. And we already have non-blocking I/O considered. And the multi-layer caching is no problem. You already know how to do it in Lua. And security is, again, simple because you have FFI, you can do NEC encryptions there. The usability is a much bigger improvement because basically you want to do scripting as configuration, just like engine script NGINX released today, right? Because everyone wants to know, hey, I want to change the logic really easy, not really just going to understand this module, HTTP module, and I cannot do anything new to it. And even better is we have tests now. Right, OpenResty comes with a pro test framework that's pretty nice. So how do we do this in OpenResty or NGINX Lua? In a nutshell, it basically says, let's just write the C callback in Lua with almost no performance hit. But also there's some nitty-gritty details in there. Basically, I follow the lead of Etran, our lead engineer, who has already done some work on lazy loading of certificate. It's essentially doing is, because a CloudFlare will handle tens of millions of certificates at the same time, we cannot stuff all the certificates in the memory, so we do lazy loading, which basically means we want to, at TLS handshake time, we decide which certificate should be used. And let's actually translate to some fork at OpenSSL. Here what we see is a simplified TLS server-side state machine. Basically, the state machine says it will have a read state. Basically, will do some CPU work, process the message, and prepare the server message. And it will goes to wait for it will send a server message. It will go to a wait for send state, and it will goes to wait for receive client message state. And also here we have a wait for certificate callback state. That once we want to do lazy loading, we have to do this non-blocking I/O there. And once the certificate callback returns, we go back to process client message. And for the session I/O, we are talking about the session caching. We just need to add a new state to it. Here, the new state is wait for session, basically. If in the rest state, if we're doing the process for client message and we want to look for the session by session ID, we will just enter this wait for session state and return to NGINX. And NGINX should be able to know that to restart the TLS handshake. As we can see here, this is the standard state machine of NGINX. Essentially, we just need to let the event handler to know that the handshake is doing some, is still ongoing with some I/O, that you have to retry it instead of just exit, right? So to accomplish this goal, we have patches in OpenSSL that we ported from Boeing SSL, which support asynchronized session I/O during the TLS handshake. It's under 100 lines of code change, and also we do some debugging, so you guys can be sure they are at least running in production now for CloudFlare. And there's one NGINX patch on top of the SSL certificate by Lua patch, which is essentially just 2 lines. So this is small enough that when, as a developer, when you go to touch those patches, you have certain level of confidence that this is not complicated. If there's anything wrong, I can understand what's going on, right? And the meat of writing the Lua code as a C callback is all in this GitHub OpenResty module. I'm supposed to open source this today, but unfortunately this is still under the private review with Yichun. But I promise I will release this code at the end of the month, or at the end of next month, because there are just a lot of work. We have to separate the logic we done in CloudFlare and just have to separate all those commits from internal code base, but it's not complicated. You guys will see, and it has tests that you can run the test with it. So the demo is, that's the end, is how we did session ID resumption in NGINX conf. Essentially, it's 3 lines of new directive. You see that we have a SSL certificate by Lua, which is basically called lazy loading. We have SSL store by Lua, which is invoking a Lua script and run the store function, and at the time of resuming session ID, you have shared dictionary. You have the fetch function there. So they are small codes, so you guys can understand. When it comes to session ticket resumption, I think I'm going over a little bit slow here. I will speed up a little bit. When it comes to session ticket resumption, we initially think it's fine, like we just have this server to read the key from this joint memcached interface, right? And when we look into how the ticket key rotation is being done, that if we config a session ticket key through NGINX conf, essentially we have a key array embedded as OpenSSL extra data. Thanks to Piotr's patch, that we can use this array to do some magical things. Because if we want to use a new key, you essentially just insert the new key into the top of this array. And the first element of the array is automatically used as encryption key for encryptions. And all the keys inside the array we're using for decryption. So consider that you want to do a rotation, you just add these new keys into the array, then automatically those old servers, although they are still using key 0 here, they can still talk to the new server using the new key because the key 0 is still in the array of the new server. So they can decrypt the key and do this re-encryption of the ticket, session ticket. So we go further and we think, do we need to lock the array to do this update? Because we are worried about halfway through the update and some TLS handshake comes in, they try to use the ticket key, and we are running into a weird state. But turns out I think we are okay here, as long as you have a copy of the new key in the decryption portion of the session array, the key array. That if you examine this sequence at any time, any server, we consider these 5 states, that any server in each state can talk to the rest of the forward server at the same time. Because if the new key is not being activated, we have a key 0 and the decryption portion. If the new key is being activated, there is a new key in all the there's a new key in all the decryption portion of the array. So we accomplish this mutual interoperations just through a little bit engineered update loop. So at the end is we think, we can just modify code to accomplish this session ticket key update. First thought is, of course, should we do this in C? It's possible, right? We just need, again, a memcached interface. We want to consider blocking I/O. We want to use a timer, and we may want to use a ticket key encryption there because, again, now you have a key schedule running somewhere. You want to do a protection of the key, and also the configuration things. So we just say, well, since we already done the session ID, how about we just do it in NGINX Lua again? Right, we already have all the things we have. And even better is, if we think deeper to this problem, that we don't need to modify NGINX or OpenSSL at all, that you just start OpenResty NGINX Lua timer that will update the array as we talk about asynchronously, and you make a timer and it will automatically restart itself from time to time, and problem just solved. So I want to talk about a little bit about CloudFlare here. Is we even go further with the ticket key because CloudFlare using Anycast, and we have multiple point or present POP around the world. So for example, here we're talking about Hong Kong or Singapore POP. By having this master ticket key schedule, and you synchronize this key schedule across the POP, then make sure that you can drop one POP for maintenance, and all the users can automatically redirect to the other POP by Anycast. And their session resumption is actually possible through session ticket key. So through session ticket. We cannot guarantee ID anymore because ID, we're talking about each pub has its own session cache. But we can still do it for a session ticket because we can synchronize the ticket key across the pubs. That makes our SRE life much better. And we also find something even better with our infrastructure is if we take sneak peek into TLS 1.3 today, they are talking about a new session resumption mechanism. Essentially, it's a combination of text session ticket key and session ID. We think about the session ticket is you essentially hand over the session secrets and ask the client to maintain it. And that's why the session ticket key is very crucial. It's very important to rotate it. If we only do session ticket as the encryption of session ID, not the key itself, we're talking about we have multiple benefits here. First of all, the client is not going to hand over a session ID in plain text. Now the adversary only see an opaque ID through the handshake. So the adversary cannot know that a session ID is being reused over time. And also we can use and also there's no session key encrypted in transition. Key either lives in client or it lives in server. Well, there's no any form of the key live through the TLS handshake. It's much more better, right? The new TLS handshake, if we look into it, our infrastructure at CloudFlare actually is compatible with this new mechanism. Essentially, we just need to modify, actually there's very little modification we need here because we just need to keep them both running at the same time and problem solved. Because ID, you looked up at a shared cache, tickets, you talk about just rotate the ticket key. So the work is not done by me only. It's a joint work. I want to thank my team here, Yichun, Nick, Xuxing, Jiale, and Guanglan, and also Peter, for getting everything running here. So I'm basically just a gatekeeper. So let's just have a quick summary of what we did today. Is we talked about cross-host TLS session resumption through session ID, and to this end we have a new NGINX Lua directives. You guys can check it out in 1 week or in 3 weeks on GitHub. That you can use these new directives to do session resumption. But there's a catch. You still need to apply the patch in NGINX or OpenSSL. But you guys can research that and tell us what you think. Also, this mechanism will be compatible with TLS v13. As for now, it's still a draft right now, but we are comfortable that it's going to be compatible eventually. And for the session ticket key resumption, we just discovered that we don't need to do anything to NGINX or OpenSSL, and we just scripting in a standard OpenResty directive enabled by Lua and enabled worker by Lua that actually does the ticket key update for us. And also this mechanism, it will be TLS v12 compatible. So here's about it. I think I have 5 minutes for questions. Yes? The question is the OpenSSL patch going upstreams? We still don't know because it's a little bit tricky to say right now. The OpenSSL, we have to present basically we want to, someone has to push it to have a new callback or like a new format, a new state machine changing for OpenSSL. We're working on that. Of course, we don't want to have patches in our code. And that's why if you guys actually follow OpenResty, that the lazy loading branch of the Lua NGINX is still a branch. It's not in the master because we need a patch in NGINX. So we're actually looking for patching NGINX OpenSSL. But if we can do that eventually, yeah, it will be better. But if they cannot, I'm still hopeful that those patches are small enough you guys will apply it. Because I drink the Kool-Aid already, so anyway. Any questions? Yeah. Yes?
Are you going to have these slides online?
Yes. And it's going to be published as well. It's a problem, no problem. Oh yeah, I have slides reserved for you. That's why we do multi-layer caching. And also we want to do, we cannot, of course, spend microsecond level for network retrieval of sessions. So we have local cache, Lua cache, worker level cache. So the worst case is still bad, but it's pretty rare. Yeah, if it failed means of course, if the TLS handshake resumption doesn't work or the server says it's not able to resume the session, we still need to restart it. Yeah, but it's not the end of the world. I think we're just improving on the existing solutions. So, yeah. Yes?
Why did you consider using Intel's asynchronous?
Can you repeat the question?
Why did you consider using Intel's asynchronous?
Asynchronous OpenSSL patch. Layer 1? The state machine you're talking about? The question is, why do we need to modify the state machine?
Why didn't you use the async OpenSSL patch from Intel?
Why don't we?
Why didn't you use the OpenSSL patch from Intel?
From Intel? Sorry. The question is, do I use the Intel's patch of OpenSSL? Not yet. I am still checking it out. Because I didn't know. I would definitely use it if it's possible. Yeah. Okay. Okay, question.
Without using something like Wireshark, how can you test to see if your sessions are correctly being resumed, either through ticket or ID?
Oh, good question. The question is how are we going to test the session resumption is actually working. So we did it through server logs. If you in a test environment, you can say server log to really detail, and NGINX will actually print out all OpenSSL log. OpenSSL log will be distinctive if it's a session resumption or it's a session handshake. Basically, the handshake, because if it's a resumption, you only see one round trip, and OpenSSL will really jump to finish stage. If it's TLS handshake, it will send like client session message, send server key exchange message. So you can just monitoring layer let you know like, oh, okay, the server is doing resumption already. Yeah.
So there's no NGINX built-in variable or anything?
I think we do some in-house logging layer, but I'm not sure NGINX is doing that. Yeah. Only touching NGINX for a year, so not really like an expert to talk about how NGINX works. Okay. Okay. Yeah, more question.
So did you say that because we're actually using the SSL branch, and thank you very, very, very much for it.
Okay.
Did you say that it's dependent on the upstream NGINX patch before that gets pushed into the master?
I think that's each one's decision. My understanding is because we always want OpenResty to be compatible with mainstream or NGINX. We don't want to do like, you want to use the master branch of the software, you still need to do some patchwork. It's not user-friendly, basically. So this branch is for expert only. So I guess you can consider yourself an expert, so that's it. All right, thank you very much.